So, in the last class, we have discussed about self-induction. Actually, it was just started. You know well that self-induction is an electromagnetic phenomenon of inducing EMF in the coil due to change in current, due to change in its own current, and hence magnetic flux changes in the coil. And the induced EMF in the coil, which arises because of variation of current flowing through the coil, is always oppose the growth or decay of current in the coil, and hence delays the current to acquire the maximum value. It means this opposite EMF that get induced due to variation of current in the coil itself is basically opposes the flow of or supply of current from the external source, and hence it behaves just like a resistance, and we say this resistance as inductive reactance, because this opposition arises because of induction. So this types of resistance or opposition offered to the flow of current through the coil is called inductive reactance, and it will have same unit and dimension as that of the resistance. So inductive reactance, we have to calculate the expression for inductive reactance. You know well here. Self-induction is also called inertia of electricity or electromagnetic inertia because it opposes the growth and decay of current. Now let us check out self-induction. If you take a coil of single turn, and current passing through the coil is varying, changing, if you say that alternating current is supplied through the coil, then magnetic field due to the current flowing through the coil will go on changing continuously. Therefore, flux or field line crossing through the coil will go on changing. As a result, an additional EMF in opposite sense will get induced in the coil with opposite polarity with respect to the supplied source or power supply to the coil. So if you say in the previous section, we know that magnetic field due to a coil solenoid is given as B equal to mu naught Ni, where mu is constant, mu naught is constant, N is also constant because number of turns. Only variation is there in I, and area of the cross section of the coil is also constant A. So magnetic flux phi equal to B dot A, that is BA cos 0 degree, and hence BA. Now placing the value of B as mu naught Ni and A as pi r square, then you will see that R is constant as radius of the hollowness of the solenoid, cylindrical solenoid. Then R is also constant or area is constant. So flux is entirely depending on current, because everything is constant there. Mu constant, mu naught constant, n constant, and A constant. So only flux will depend on I. Hence, magnetic flux changing through the coil due to its own current, due to changing its own current, is directly proportional to current through the coil. And hence, phi equal to Li, where L is proportionality constant and is called inductance of the coil or inductor. For I equal to 1, that is current equal to 1 ampere, then L becomes equal to flux. So you can define that the self-inductance or coefficient of self-inductance. This L is proportionality constant and is called coefficient of self-induction or simply called self-inductance. So self-inductance is defined as the magnetic flux linked with the coil when unit current flowing through the coil. So you see here L is the constant and proportionality constant and is known as self-inductance or simply coefficient of self-induction. Now what about its definition? If I becomes 1 ampere, then L becomes equal to flux, magnetic flux, and hence self-induction, coefficient of self-induction or self-inductance is defined as the magnetic flux linked with the coil when unit current passes through it. So self-induction is that much flux linked with the coil when 1 ampere of current passes through the coil. Now, we know from Faraday's law of electromagnetic, EMF induced in the coil will be negative rate of change of magnetic flux. So here phi equal to Li, so EMF induced equal to minus d phi by dt. So differentiating both sides with respect to t, so we will get here d phi by dt equal to di by dt into L, because L is constant, so L can be taken out of the differential operator. So here E equal to minus L into di by dt. Minus sign indicates that whatever EMF supplied to the coil, induced EMF will be opposite to that of the supplied EMF, and hence this induced EMF will not contribute to the current or EMF or voltage provided to the coil or circuit. Instead, it will oppose the flow of current through the coil, because this is opposite to the supplied EMF or supplied voltage. Now, try to understand, if di by dt equal to 1, if rate of variation of current is equal to 1, then coefficient of self-induction just becomes equal to induced EMF. Here we have seen that coefficient of induced EMF just becomes equal to magnetic flux, and now here it becomes just equal to induced EMF. So now we can have another definition of coefficient of self-induction or self-inductance. So self-inductance or coefficient of self-induction is defined as that much induced EMF set up in the coil through which the rate of variation of current is unity. Okay, now come to the point. SI unit of coefficient of self-induction or self-inductance, that is L, is said to be Henry. Henry is the name of scientist. SI unit of self-inductance is Henry, and it is written as in a full form HENRY, and in short it is denoted by capital, because it is name of scientist. So if it is abbreviated, then it must be written capital, and in full form it is started with a small. So self-inductance is said to be 1 Henry when 1 ampere of current in a coil links with a magnetic flux of 1 Weber. So you see here phi equal to Li. So when I becomes 1 ampere and phi becomes 1 Weber, then L is said to be 1 Henry. That is Weber per ampere is called Henry. If you say L equal to phi upon I, then unit of phi is Weber and unit of I is ampere, then L equal to Weber per ampere. So Weber per ampere itself is called Henry. So you must learn that Henry has been given a name in respect to, of that scientist, but in actual sense, this unit is Weber per ampere. Weber per ampere itself is called Henry. So self-inductance is said to be 1 Henry. Now we take another definition, that is from here. E equal to minus L di upon dt. If you take this, then we define in another way. Self-inductance is said to be 1 Henry when unit rate of change of current, that is current changes by unity as 1 ampere per second and induces an EMF of 1 volt in the coil, then self-inductance is said to be 1 Henry. Here again you will see that unit of Henry will be, you see here, L equal to EMF divided by di by dt. EMF has unit voltage, volt, and di by dt has unit ampere per second. So second will come to numerator. So voltage into second divided by ampere. So here Henry is just equal to volt second per ampere. Now come to the point, self-inductance of a solenoid. Because solenoid itself behaves as an inductor. So solenoid can be used to store electrical energy in the form of magnetic energy. That means when a solenoid is connected with the external supply of current, then current get converted into magnetic energy and get in uh, stored in the space between the solenoid, and that can be used for future purpose. So when you cut the supply of current in the solenoid, you will see that the stored energy in the solenoid will start flowing in the circuit even after removing the power supply. So try to understand here, magnetic field due to solenoid is given as B equal to mu naught Ni, and magnetic flux linked across one turn of the coil is given as B dot A, that is BA, because the angle between magnetic field and area vector will be 0 degree, because area vector is directed in this direction here, and magnetic field line is also directed in this direction. So here mu naught Nia. You see here A is constant because geometry of the solenoid is constant. So A will remain constant, that is the area of cross section of the solenoid will remain constant. And N is the number of turns per unit length of the solenoid. So this N will also remain constant, and mu naught is the magnetic permeability of the vacuum. So this will also remain constant. This implies that flux will depend only on I, that is current. So flux per unit length of the solenoid will depend only on I. So you see here phi proportional to I, keeping A and mu naught constant. So A and mu naught is nothing but what? If you compare with this expression or with this expression here, then you will get that phi equal to L here, and you put the value of phi from here. You put from value of phi from here, mu naught n I a, then placing this value here, phi equal to mu naught n I a equal to Li. So I will get cancelled. So L equal to mu naught n I, sorry, n into a, mu naught n into a, where n is number of turns of the coil per unit length, and A is the area of cross section of the coil, and mu naught is the magnetic permeability of the vacuum. So inductance depends on the factor area of cross section of the coil and number of turns of the coil, as well as magnetic permeability of the material inside the coil. So if inside the coil no material is inserted here, no material is inserted inside the coil, then magnetic self-inductance depends on only area of cross-section of the coil. When iron is inserted, then mu naught will be replaced by mu, or relative permeability. Then self-inductance will get changed. So you know that magnetic flux linked per unit, magnetic flux linked with the single turn of the coil. But in the L length of the coil, there are so many turns. So you divide here, total number of turns of the coil is capital N. So number of turns per unit length is equal to capital N divided by L equal to a small n. So in place of a small n, we place here capital N divided by L. L is the length of the solenoid here. So we see here, by comparing this one, this is the magnetic flux. This is the magnetic flux linked with this coil. How? You see here. Try to understand. Because this is the flux due to single turns, has already been given here, due to one turns. Then what happens to the flux when there is n turns, capital N turns? So this single turns is multiplied by capital N, so here becomes n square. So mu naught n square into I into A divided by L. This is the magnetic flux. Now comparing this magnetic flux for the expression of flux here Li, then I will get cancel out, and you will get that L equal to mu naught n square A divided by L. So this is the expression for self-induction. That is mu naught n square A divided by L. And if you place, multiply and divide by L both sides, then you will get, instead of capital L, you will have a small n, and hence mu naught n square A into L here. L will come there. So I think that you must have understood well. And now we have to calculate the energy storage inside the solenoid, how energy gets stored inside the solenoid. So far we have learned about the expression of coefficient of self-induction or self-inductance. Now we have to learn about the energy stored in an inductor or in a solenoid. Let us check out. Energy, this is the expression for energy stored in a solenoid or an inductor. As we have already discussed that whenever current supplied to the solenoid, electrical energy get transformed into magnetic energy and get stored in the space in the solenoid, a space available in the hollow of the solenoid, hollow space available there inside the solenoid. Now Let us check out a small amount of work done in establishing a current in the coil in a small time dt. So far we know that electrical power dissipated across the solenoid is given as induced EMF E into I. You know that power equal to V into I, voltage into current equal to power. So this is E into I. E is the induced EMF and I is the current, induced current in the solenoid. So product of induced EMF and induced current is just equal to uh, induced power, and so power when multiplied by a small interval of time dt then becomes 1, because you know that dw by dt equal to power ei, so dw equal to ei into dt. ए लड़का मोबाइल फोन ले जाओ. Now you see here, now we have to integrate this expression because this is differential work done for differential time interval. So in place of E, I and dt, we can place E equal to what? From here you can see E equal to what? Minus L into di by dt. So you place here in place of E minus L into di by dt. So dt will get cancelled out and you will have L into di, L into di, and now integrating this, now integrating this from the limit as current started growing from 0 to maximum value. So maximum value of the current that is grown up in the solenoid is I naught and is called current amplitude. So its lower limit will be 0 and upper limit will be I naught, and placing this L is constant, so taking out L outside the integral sign and then integrate I into di, you will get here half L I naught square. It is clear that magnetic energy stored in a solenoid depends on coefficient of self-induction L or inductance L and current amplitude I naught. And this expression is similar to that you have studied in a capacitor, that energy E equal to half epsilon naught E naught square in case of capacitor. So this is analog of that one. Now, so far we have discussed about self-induction. Now we will discuss about mutual induction. Here, in this case, only single solenoid were taken. So if current I flow through this solenoid, due to variation of its own current, EMF get induced in the solenoid. This is called self-induction. Now, here in this case, we will take two solenoid. In one solenoid, current is allowed to be varied and other solenoid will not be connected with the power source, and hence due to variation in current in one solenoid will causes change in flux in the second solenoid, which are not in actual contact with the first one. And in this case, due to variation in the current in one solenoid causes induced current in the second solenoid, and in turn second solenoid also induces current in first solenoid, and this is called mutual induction. So mutual induction is the phenomenon of inducing EMF in the secondary coil due to change in the current in the primary coil, and in turns secondary coil also induces current in the primary coil and hence magnetic flux in the secondary coil. This is called mutual induction. So let us check out. Take two coils with coefficient of self-induction L1 and L2. So magnetic flux linked with the second coil because of variation in current I1 in the first coil is denoted by phi 2 1. Phi 2 means a magnetic flux in the second coil due to variation in the first coil. That's why here it has been written subscript as 2 1. So phi 2 1 is proportional to I1 because current I1 in the first coil is varying. So flux is getting changed in the second coil. That's why EMF will get induced in the second coil. So here phi 2 1 will be equal to MI1, where M is proportionality constant and is called coefficient of mutual induction or mutual inductance. Now, if I1 equal to 1 ampere, then M equal to phi. That is, mutual inductance or coefficient of mutual induction is defined as the magnetic flux linked with the secondary coil when there is unit current flowing through the primary coil. And in second terms, according to Faraday's law, if you differentiate this flux with respect to time, then d phi 2 1 by dt equal to dmi1 by dt. As m is constant, so m can be taken out of the differential operators. So here will be m into di1 by dt. So you will see that EMF induced in the secondary coil is given as E2 equal to minus d phi 2 1 by dt equal to E2 equal to minus m into di1 upon dt. So if di1 by dt becomes 1 ampere per second, then coefficient of mutual inductance or coefficient of mutual induction M is just equal to EMF induced in the secondary coil. So in this context, we can define mutual inductance. Mutual inductance or coefficient of mutual induction can be defined as the EMF induced EMF set up in the secondary coil when the rate of change of current in the primary coil is unity. Then this EMF is just equal to coefficient of mutual induction. SI unit of mutual induction or inductance is also Henry. And now mutual inductance is, in second context, we can also define mutual inductance is said to be 1 Henry when 1 ampere of current in the primary coil is linked a flux of 1 Weber across the secondary coil. This is according to first expression, this one. And now according to this expression here, this is the another definition. Mutual inductance is okay. Now let us start. So mutual inductance is said to be 1 Henry when unit rate of change of current 1 ampere per second, that is di1 by dt is equal to 1 ampere per second in primary coil induces an EMF of 1 volt in the secondary coil. Then a coefficient of EMF is a coefficient of mutual induction is said to be 1 Henry. Now we have to derive the expression for mutual inductance or coefficient of mutual induction. So we take here 2 coil, because while we are talking about mutual induction, it is essential that there must be 2 coils so that there could be a mutual interaction. So here 2 coils, one of red one and other one is of blue one, in order to distinguish visually. and with same area of cross section. Both the coil will have same area of cross section. So magnetic field in the first coil due to current I1 flowing in it is given as B1 equal to mu naught and N1 I1, where N1 is the number of turns per unit length of the primary coil or first coil. So magnetic flux linked across one turn of the secondary coil is given as d phi 2 1 per unit turn B1 into A, so mu naught N1 I1 into A. And if you want to replace the number of turns per unit length N1, small n1, you can write here capital N1 by L. So mu naught capital N1 into I A divided by L, that is length of the coil. So magnetic flux linked, this is the flux linked due to single turn of the coil. So magnetic flux linked with the n turn of the coil can be obtained by multiplying by N1. So here you have phi 2 1 equal to mu naught N1 N2 I1 A divided by L. And but on comparing this expression and this expression, you get M2 1 equal to mu naught N1 N2 A by L. And again you can replace N1 with the help of a small n1 into L, then you will get here mu naught N1 N2 A into L. So coefficient of mutual induction will depend on number of turns per unit length of both the coil, and area of cross section is common in both and length is common in both. Length could be different for if the length of the two coil is different, then we will use different length. For first one we will use L1 and for second one we will use length L2. But here in the two coils length is same, so we will use L, and in two coils area of cross section is same, so we'll use A. So we see here as same current flows through the coil, so coefficient of mutual induction in the two coil will be same. That is M21 is just equal to M12 and hence is equal to mu naught N1 N2 A into L. So for two long coaxial solenoids of the same length and same area of cross section, the mutual induction or inductance is same and leads to the principle of reciprocity. That is M equal to M12, that is coefficient of mutual induction in the secondary coil. In the secondary coil जस्ट क्लास लेकर के हम बात करते हैं, ठीक है. In the secondary coil, in the primary coil due to secondary coil, and second one is in the secondary coil due to primary coil. So this mutual induction will be equal. Now here additional information to be given. If the two solenoids are wound on a magnetic core of the relative permeability mu r, that is iron rod is inserted in the two coils, then mu naught will be replaced by relative permeability into mu naught, that is permeability of that medium. So if you insert a magnetic material inside this coil, then expression of mutual induction becomes like this. And if the solenoid S1 and S2 have number of turns N1 and N2 of the different radius R1 and R2, then coefficient of mutual induction becomes mu R into N1, N2 divided by pi R1 square divided by L. So mutual inductance depends also on the relative placement of the solenoid. These are the factors that mutual induction depends on. Coefficient of coupling between the two coils having self-inductance L1 and L2 and mutual inductance M is given as K equal to M divided by root under L1 into L2. And in generally, value of k is more than smaller than 1, and if L1 and L2 are connected in series, because inductor is a two terminal device and it can be connected in series and parallel just like resistor and capacitor. Therefore, inductor can be connected in series just like resistance, as resistance was connected in series as an equivalent resistance was given as R1 plus R2. Here, equivalent inductance will be given as L1 plus L2. And if it is connected in parallel, then equivalent inductance will be given as 1 by L equal to 1 by L1 plus 1 by L2. And related with this, we have already shared notes of combination of inductors in series and parallel. I think that this chapter has been completed, and now we will start new chapter, alternating current. I think tomorrow I will start new chapter, and I will send you the notes related to and question sets related to this chapter tomorrow. Okay? Hello? Am I audible to all of you or not?
Yes, sir.
तो ये टॉपिक कंप्लीट हो गया, मुझे लगता है वही 1-2 मिनट बचा हुआ होगा, ठीक है, क्योंकि ऐसे भी अपने आप ये खत्म हो जाएगा. तो नेक्स्ट डे हम न्यू चैप्टर स्टार्ट करें या फिर इस पर कुछ डाउट क्वेश्चन है वो डिस्कस करें?
सर रिवीजन करवाइए ना, कितना आगे बढ़िएगा.
हाँ जी, क्या बोल रही हो?
सर फिर से पढ़ाइए यही चैप्टर को.
इसी को फिर से रिपीट करें?
यस सर.
देखो, फिर तो रिवाइज हम करेंगे ही, एक एक चैप्टर फिर से रिवाइज करेंगे, बिकॉज देखो अभी हमारा टारगेट ये था कि अगस्त एंड तक हमारा इलेक्ट्रोमैग्नेटिक वेव तक खत्म हो जाना चाहिए, जैसा कि ट्रेडिशनली होता रहा है, ठीक है. तो ये खत्म होगा, चूंकि आपका आगे का सिलेबस भी तो बचा हुआ है, समझ रहे हो? इसमें बोलो जहां
यस सर.